Hey everybody, just wanted to do a little video here, short video on going over that worksheet I had in class there. So the work power energy practice test that I gave you guys. So I just want to talk about a couple of problems or talk about all the problems and let's take a look. Let's keep this short. All right, so pendulum problem. So they give you the length and they give you the mass. Interesting. Don't always need the mass, right? The bob is released from an angle of 30. And what is the vertical height when the bob is released? So, all right, so find H when you have this at 30 degrees, all right? And then what is the speed at the bottom of the swing? So a full swing. So anyway, I drew a little bit of a picture here. So first, this part here, this is the 30 degrees, and it's going to be a full swing, right? You're going to have a full energy transfer down to the bottom point there. What is height? Height is L minus L cosine theta. You have height. So it's pretty quick to find height. In this case, you just do 0.75 minus 0.75 cosine 30, L minus L cosine theta, and you'll get the height. Anyway, so the height is 0.1. That was part A there. Speed at the bottom, well, when you have an mgh to a 1/2 mv squared, you can cancel out and go right to v equals radical 2gh and just put in that height change there, 0.1, gravity 10, 2, you get a velocity, I got it there, 1.42. C, I thought there might be a little confusion on what C was asking, so I thought we would just spend a moment talking about that. So in C, it says, what's the speed when the rope is at 15 degrees? So you can see I have two answers here, really. I thought some people might interpret that as you're just taking it to 15 degrees now and then letting go. So it wouldn't be going as fast as before. Turns out it's about, I think it's half the height, but you get to a much slower speed. You just find out the new height at 15 degrees, L minus L cosine theta. Anyway, you should figure out if it's a full swing. If you interpret it as pulling it back 15 degrees and letting go and seeing how fast it is, it should be going 0.72 meters per second. The question is supposed to be much cooler than that. It's supposed to be more like, as it swings past 15 degrees, how fast is it moving? So we mean you pull it all the way up to 30 and you had let go, and how fast is it moving as it swings through 15 degrees? So pretty neat. A couple of ways to think about it. I made a little bar chart of one way to think about it, is that it had just potential up here, and then when you let it swing down at 15 degrees, it kind of has both. You could kind of consider the 15 degree height to be a zero height, and you could just kind of figure out the height it's going to lose and what velocity it should gain then. But it makes a bit more sense to me thinking about the full amount of potential, and then as it swings through 15, it still has height, but now it has motion. It'd be an mgh. Mgh at the beginning would equal mgh and 1/2 mv squared at the end. You'd figure out that new height at 15 degrees, L minus L cosine theta. Anyway, so you'd have the initial height, and then height 2, I was kind of calling it, for the height at 15 degrees, and then solve for the v there, you get the velocity. If you do it that way, you get 1.22 meters per second as it swings through 15 degrees. Seems kind of fast, if it only gets up to 1.42, would it get up to 1.22 here? Yeah, that makes some sense. Remember, as you're falling, you're not really moving fast at the beginning, and then you're going faster and faster and faster, so you start covering the rest of your distance much more quickly, in less time to accelerate. So I don't know, I like 1.22, and that's what I get on the math side of things. Anyway, that was the deal with number one, or what was that? Number one. Yeah, all right. So cool, try it. Two. This is one I was kind of talking about where we give you some information to sort of figure out a spring constant, and then you kind of do something with that spring constant depending on what the problem is talking about. So with those ones, they tell you like something to use, kind of Hooke's law. Hooke's law was that F equals Kx. So F equals Kx. They give you something to kind of figure out this K, and then they ask you something, something energy-wise about, using that K value, obviously. So when this one, they're giving you info to figure out the force is really just hanging that first mass on there. So a student, takes the spring, and then they go ahead and hang a mass on that spring. When they hang that mass on that spring, it's going to stretch the spring, and that's what they're telling you at the very beginning. So it really, what's the force? It's the weight of it. So if it's 0.4 kilograms, we would go with gravity 10. We would say 4 newtons. 4 newtons. What's the K value and how far does it stretch it? So 8 centimeters would be 0.08 meters. and you get a K value. What did I get? I put it there, 50 newtons per meter. And then it goes on and says somebody then does 15 joules of work. How far did they stretch it? So you just put that 15 equal to 1/2 kx squared with your new K value, and you should get that kind of distance. Cool. Three, care package. So it's something being dropped from an airplane here. And it tells you the mass of it, gravity, Earth here, and it gives you the height. And then it says on its way down, it's going to have some air resistance. So 65% of its initial PE is lost, to air resistance, air friction. So as it falls. So what is KE on impact? So, KE on impact in a vacuum would have been whatever PE was at the top, potential energy at the top. So really just figure out potential energy at the top, 20 times 10 times 125. I have that somewhere. Yeah, is that 25,000 joules? And then if you figure out 65% of that's lost, or take your 25,000 joules and multiply by 0.35 and figure out what's left. Anyway, that's where the 8,750 comes from. Set that equal to 1/2 mv squared, and you can pull the V out of that thing. Go for it. 4, what's up with 4? This one. So this is one of these work is the change in energy problems. So it's a change in kinetic energy here. So it talks about the mass of an automobile, speed from 10 to 30 in 1.8 seconds. How much work is required? So work would be the change in energy. Figure out the final energy, subtract the initial amount of energy, and you would have the work done. So do 1/2 mv squared at 30, 1/2 mv squared at 10, subtract those, figure out what the change in energy is. I had that somewhere. Yeah, I think that was a change in energy of 480,000 joules. There it is right there. And then if you divide by time, you can figure out power is work divided by time. So if that's the work that was done in that amount of time, then you can figure out sort of that's the power. If that is the maximum power, it says then, so if the car could apply that amount of force, or power in a sense back, how long would it take to change speeds from 30 to 50? Now, what's interesting is these are both a change of 20 meters per second, but they're very different energy-wise, right? And work has to do with change in energy. So it's not like, oh, this is a 20 meter per second change, it's going to be another 1.8 seconds. No, it doesn't. It's going to take a different amount of time. It's going to take longer, actually. This is a different amount of energy. So you have to kind of figure out, what's the energy change going from 30 to 50, 1/2 mv squared minus 1/2 mv squared. Figure out the change. Consider the power is work divided by time. Solve for time now using the power from before. And it's going to take double that amount of time. So it only takes 1.8 seconds to go from 10 to 30, but it takes 3.6 seconds to go from 30 to 50. Even though, once again, they're the same velocity changes, they're different amounts of energy. Anyway, pretty cool. Oh, I like this hiker problem. That was pretty sweet. So this was a kinetic energy. They're going to grab the rope, swing out, and then have a certain amount of potential energy at the maximum swing height. They give you the length of the rope. They tell you this horizontal distance. A lot of these pendulum problems will just tell you the angle, or it might be something where you have to do just a little bit of trig, having the, adjacent and opposite angles. Is that what you have? Yeah, careful. All right, hold on a second. Yeah, the length, the adjacent, and then the opposite. Yeah, so figure out the angle that way. Anyway, question is asking, though, what horizontal speed would you need here, part of your kinetic energy? What speed would you need to have the amount of energy stored there? So basically, you want to figure out, what's the angle you're swinging to based on this 1.8, and knowing that the length of the rope is 4 meters. You can figure out the angle. I wrote it down somewhere, 26.7 degrees. So then at 26.7 degrees, what kind of height does that give you? Because we need to know what energy do you end up with to then go backward and figure out what kind of velocity do you need, to have the kinetic energy at the beginning. So at 26.7 degrees, you can figure out height. Height is length of the rope minus length of the rope, cosine the angle, and you can get the height change. So then it's really just 1/2 mv squared to an mgh, or cancel the masses out. Half v squared equals gh, or v equals radical 2gh. Anyway, you get a velocity of 2.92 required in order to swing up to that height. That would give you the angle. That would give you that horizontal distance. Awesome. All right, what else is going on? Oh, roller coaster. Here we go. So what was given to you in the chart, if you noticed, is the thing that is not in red. The thing in black over here is that they were starting from rest. So TE, by the way, is total energy. So potential energy at the beginning, yes, MGH based on the mass of the rider. So we're going with the rider's kind of energy through here, and that works. You can do the whole cart as well, and that works as well. Remember, mass is really not important, if you remember, with a lot of this stuff. Kind of neat the way that cancels out. A little counterintuitive. Anyway, so total energy. So your total energy for this kind of roller coaster ride is that whatever your potential energy is here, that is your total energy for the ride. You're not moving. It says velocity is 0. MGH gives you 24,000. That's your total energy. You got none for movement. B, total transfer, right? No friction with these. Or did it even say? Yeah, we don't do friction with these. Totally down at the bottom there. So you got no potential energy. Full transfer, 24,000 is now moving energy. Put that equal to 1/2 mv squared. And you've got your velocity of 24.5. Should be going slower because you got to trade a lot of that velocity back for height in the loop. So how do you find kinetic energy there to get velocity? Well, you know that the total energy is never changing. There's no negative work happening here, with air resistance and frictions and things. We do these again frictionless. Anyway, so total energy never changes, notice. And so you can figure out the MGH here, which is 20,000. And if there's only 24,000 available, 4,000 must be in the form of movement. Put that equal to 1/2 mv squared. You've got your velocity at that height. Lovely. Same answer if it was not a loop or a hill. Again, real life would have very different frictional things going on and would have quite an effect. Anyway, what's happening? Roller coaster. What do we got? One more? Oh, that was it. Awesome. All right. Have a great weekend. Email me any problems. Do my best to help you out. All right. Later.